Welcome to our Colloquium series. I'm happy to introduce Professor Lillian Ratliff, who joined us in the fall of 2015. So Lillian comes from Berkeley, where she worked on incentive mechanisms for applications that are shared in the economic domains. So she is going to be talking to us about incentive mechanisms for smart connected community infrastructures today. She holds a bachelor's in electrical engineering and a bachelor's in mathematics from UNLV. She also holds a master's degree from UNLV. That's in electrical engineering. Yes. And she has, after her PhD, she was a postdoc with the same group at Berkeley. This is the Control and Dynamical Systems group, a group of faculty who are good collaborators of ours, Shankar Sastry, Claire Tomlin, and a large group of others who are part of many activities that we do. So here Lillian has been working with Bao Sen and also with some of us in different collaborative efforts related to smart and connected communities or smart cities, as you have heard of. Some of the work has City of Seattle as part of the research infrastructure and the data provider. So with this, I welcome Lillian to give her talk today. Thank you.
Thanks for the introduction, Radha. Okay, yeah, so I'm going to talk about the emerging data market, and specifically adaptive incentive design for smart and connected infrastructure. And so this is largely work that I did as a PhD student and then a postdoc. The second part of the talk will be work that is joint with two graduate students here, Tanner Fiaz and Chase Dowling, as well as Bao Sen Zhang, who's a faculty member here. Okay, so our infrastructure systems are at an interesting inflection point due to the fact that we have a large amount of data, and more available computational resources so that we can better optimize the performance of these systems. And so one of the things that we've observed, and this isn't recent, but it's been happening over time, is that now with new smart technologies, for example, smart meters in the smart grid, as well as new embedded technologies for sensing cars, for example, in the road network, we're able to learn users' behavioral patterns or how they're consuming a particular resource and fold that into the way that we make our operational decisions. More than that, now that users tend to have constantly carry different smart devices with them. They've been installing smart devices in their homes. We can now provide feedback to those users. And so what this means is that the informational content of the data becomes very important in the sense that how the users are being compensated for providing their data is important. So because there is this value, this intrinsic value in the data in terms of engaging consumers and providing them feedback so that they can better consume resources or consume resources in a way that's more efficient. Other parties have been emerging on the scene, so third-party aggregators. A good example of this is C3 Energy, which is now transitioned to C3 IoT, but in their original conception, they were focused largely on energy consumption or energy, the energy sector. And so basically, and they're not the only ones doing this, but they're a good example. Basically, their business model is that they work with energy providers, and they take their data and provide them a computational platform for computing analytics that can then help the energy provider make better decisions about how to engage with their consumers, as well as at the operational or at the control of the grid level. So they've now pivoted to being broader and not just focusing on energy. As I mentioned, they're now called C3 IoT. And so there's a ton of people in this space. Another example in the transportation area is Waze. Waze is a company that you probably all are aware of, in which they're an app that provides users with routing directions, and users can provide information back, such as where accidents are located or what their experience is with a particular route suggestion. So what this means now is that we have a lot of differently invested parties interacting with each other, and the primary way that they interact with each other is through data exchange. And so what I like to refer to this as is the emerging data market. And so data markets have existed for a long time in other areas, specifically, for example, with internet-based companies and ads collecting data on how users click on different things. But it's sort of new in the space of infrastructure. And so what's important here that distinguishes this from just traditional data markets is that now there's this underlying physical system that is coupled with the cyber layer in which we have all of the data and informational constraints. So what I'll talk about today is a particular class of problems that arise in the context of this emerging data market. In particular, I'll talk about examples in which we have strategic providers of data, so strategic sources. You can think of these perhaps as energy consumers or drivers on a road network, and you have a planner who wants to make decisions based on this strategically provided data or information. And perhaps they break their decision into two things. First, an estimation or a learning task. So for example, maybe they want to classify these players and then provide them incentives based on which category they fall into. Or maybe they want to do demand prediction so that they can perform better control. And so in addition to that, they also have operations and management decision. So this might be load rebalancing in the grid or traffic light control. And so then their decision not only impacts the physical system, but also can be feedback to the users. And so that's what I'll focus on is this closed loop behavior in which incentives are provided back to the users. Okay, so in the course of this talk, I'll focus on 4 different areas. The first is an abstraction of this problem of optimizing when you have strategic sources. The second is an algorithm for this abstraction and convergence results. And then I'll provide an illustrative example, which may seem simple, but it's really a core problem or a nugget of a problem in which many other problems or applications have formed around. And then if I have time, which it may not be the case given that I only have 45 minutes, I'll talk about new work in the area of urban parking. So this will be more of an application-driven problem in which we're really focusing on developing data-informed models of parking and congestion in urban areas. Okay, so this adaptive incentive problem, this problem of designing incentives when you have a set of strategic sources, can be abstracted in the following way. So first, we model the interaction of these strategic sources or agents in a non-cooperative game in which each of them has a cost. So we model their cost as being composed of 2 pieces. One, their nominal cost, so this is just their individual preferences over how to consume a particular resource. And an incentive, which is designed by a planner. And so for the purpose of the results that I'll provide, we parameterize these cost functions. The nominal cost is parameterized by a set of basis functions in phi and a parameter theta, and the incentive mechanism is parameterized by a set of functions psi with parameter u. Okay, so then we have this a planner who is going to make a decision about how to optimize their cost. So their cost will be FP, and maybe this is this load rebalancing example or traffic light control or something like this. And so the first thing that they do is they optimize first their cost function is a function of not only their own choice variable, which we'll say is V, but also the collective choices of all the other agents, which we're saying is X. And so the first thing they do is they figure out, okay, independent of what the agents do, if I optimize my cost, what is the best thing that I can do? What is the thing that's going to be the best thing for me as a planner? And so this determines a desired outcome, XD and VD. Another example of a cost, for example, for this planner, might not be operations or management specified by some operations or management decision, but rather the social cost. So maybe you sum up the cost across all of these agents, and you're trying to do the best thing for society. And so then our goal is going to be to learn these parameters, because the planner does not know the parameters a priori. They don't know the preferences of these agents, and optimize the use such that our incentive mechanism converges to the desired value for the planner, VD, and such that the outcome of the agent's interaction converges to a desired outcome. Okay, so How we're going to break up this problem is in the usual way in which we typically do control problems where we have estimation and control task. We split the estimation and the control problems, and we address them each individually. And so basically, our goal is going to be able to come up with an algorithm that iterates around this loop. Agents play according to some model of their interaction, which I'll get into in a minute. The planner observes their response. They come up with an estimation scheme to determine the thetas. They pass those thetas into an incentive design step in which they design the feedback parameters U. And these can be, for example, they don't have to be money, for example. They could be an information structure that's implemented in the cyber layer, for example. And then this gets fed back to the agents and modifies their cost and so on. And this repeats and repeats. So now I'll go through each of the steps. I'll set up the algorithm, and then I'll provide you the results. OK, so we look at two different cases. The first case is when agents play according to a Nash equilibrium. And I'll describe in more detail what that means. But essentially, it just means they play a best response to whatever the other agents are doing. Or they play myopically. So they play according to just some simple update rule. An example of this might be that they're following the gradient of their cost. Or perhaps they're playing according to fictitious play when they look at the historical frequency of past plays of all the other agents. Both of these fall into this category. So the goal of the planner in the first step is to come up with some algorithm or an update step for updating their parameter estimates. OK, so the details of how they do that are as follows. First, they define a loss function. And so we're going to take a simple loss function for the sake of this presentation, in which we look at the difference between some observation vector and the regressor times the parameters theta, and we look at the squared loss. And we're just going to do a simple update rule in which we do projected gradient descent onto the set of feasible parameters. And I'll define what these are now. OK, so the two ways in which agents can play is either according to Nash or according to this myopic update strategy. And so Nash, in words, just means that no player can gain by unilaterally deviating from what we're calling a Nash point. So basically, mathematically, this just means that their cost, in the cost minimization case, when we model players as cost minimizers, their cost is less than any other option they could have picked, given that the other players are fixed at the Nash equilibrium strategy. And so one of the first results that we have is that we can model a new class of Nash equilibria that are a subset of the broader class of Nash equilibria called differential Nash equilibria. And so basically, these are points in which the derivative of each player's cost function with respect to their own choice variable is identically 0, and the second derivative is positive. So this is just basic results from calculus. But what's interesting is these class of equilibria are, in fact, generic among all the Nash equilibria. And if we enforce this second order condition, ensuring that they're non-degenerate, which is just looking at the derivative of this covector of first order derivatives of each player's cost. If that's non-zero, then we say that they're non-degenerate, and these are, in fact, isolated. So we can use these first and second order conditions to define our regressor and our observation vector. And so we do that as follows. So just take the derivative condition for one player, let's say player I. We set it equal to 0 with our parameterization, and we define this derivative with respect to the nominal basis functions as the regressor, and the derivative with respect to the incentive basis functions times the incentive parameters as the observation vector. And then we can define our admissible set of parameters by just setting the second order derivative to be positive and enforcing this when we choose our parameter update. OK, in the myopic case, it's very simple. It's just like you would do if you had a classic control problem in which you are trying to do adaptive control and learn the parameters of a system while also designing your control. So we just look at the update equation. We simply rewrite it in the following way to get our observation and our regressor. And then the admissible set of parameters are exactly whatever the parameter set was from the beginning. OK, so this gives us our loss function. And then we can easily just do a projected gradient descent onto the admissible set of parameters to update our thetas. Okay, so the next step, once we have our thetas, is to then pass them into this incentive design step, where our goal is going to be to select the parameters u such that we get x. Ideally, x is equal to, the updated x is going to be equal to the desired outcome xd, and the incentive mapping evaluates to vd. But in practice, what we end up doing is trying to just ensure that these get as close as possible. Okay, so the way that we do this is by first writing down the desired observation vector, which is the desired observation vector and the desired regressor. And so for the Nash case, the way that we define these is exactly as we did in the step for the updating of the parameters, except now we evaluate the derivatives of the incentive basis functions and derivatives of the nominal basis functions at the desired outcome. So this gives us Xi evaluated at xd and our desired observation vector. Then we can plug these into an optimization problem for the Nash case, in which we minimize the Nash cost. So this is just making sure that you're as close to Nash as possible in the first term. And the second term is just making sure that you're as close as possible to the desired incentive value. And if we add this extra constraint that our derivative of our covector of first-order derivatives of players' cost functions is positive definite, then we get that the desired outcome is in fact stable and isolated, which is important. Okay, for the myopic case, again, it's much easier. We just simply define the desired, this should be xd, and that should be xd. So we just define, our desired observation vector and our desired regressor, and we have a similar optimization problem where we choose the parameters u to optimize this update cost and the incentive cost. Okay, so now we just put all this together in one big algorithm, and so it goes as follows. Observe the choice that the players are making, x. Update your parameter estimate using this projected gradient descent. Choose a u that induces xd, and we get our desired incentive mapping. Feedback the u, update your k, and rinse and repeat. Okay, so then the results that we have are for this algorithm are as follows. If we make an assumption that for all 8 possible agent preferences, theta, there exists an incentive parameter such that the agents play the desired strategy. So this seems restrictive in the way that it's stated, but in fact, in practice, it's not, because we have flexibility in choosing the parameter, the incentive basis vectors, as well as the basis vectors for the nominal cost. So that allows us to be able to satisfy this for any possible set of parameters that the agents may have. So then our first result is on the convergence of the parameter estimates. So if the algorithm is persistently exciting and stable, then we get parameter convergence. So again, these two, persistence of excitation and stability, may seem strong. So persistence of excitation just means that we ensure that we have enough information to be able to learn the thetas. And the stability condition just makes sure that the algorithm doesn't blow up. Stability is easy to ensure, again, in the choice of the basis functions for the nominal cost. Persistence of excitation can be quite difficult in practice to ensure. However, there are classes of basis functions, for example, radial basis functions, which exhibit this property. Okay, so then once we have this result of parameter convergence, we can also show that in the myopic case that this directly implies, without any work, that we get the convergence of the choice of the players to the desired outcome, and the parameters u converge to the right parameter values such that the incentive mapping evaluates to VD. In the Nash case, we get a slightly weaker result, and this is because in general for games, there's a non-uniqueness of equilibria. Even for games in which all the costs are convex, you can still have non-uniqueness of the Nash equilibria. But what we can say is that if our desired Nash equilibria, which is easy to check a priori, is a non-degenerate differential Nash equilibria, and our parameter estimates are close, then there exists some Nash equilibria that's close to XD. If it turns out that it's the case that the value that the players end up converging to is, the Nash equilibrium of the true game is stable. This is hard to check in practice because we don't know what the true game is in practice. If it turns out that that's stable, then users will converge to that value under a Tatonement process or a gradient play. We can also extend all of these results to the case when you have noise under all the classical assumptions that you usually see in adaptive control, for example. So another thing that typically comes up in incentive design problems is that you would like not only for the problem to be incentive compatible, which is what we're ensuring through that the algorithm that I just described, but also that you have a solution that is budget balanced, which means that the collective cost to the agents is the same under the incentive as without the incentive, and that the agents voluntarily participate in the program, that they don't just decide, okay, well, I'm going to go and choose a different energy company, or I'm going to use a different mode of transportation, for example. And so we can easily include these objectives in the incentive design step of our algorithm by just adding them either as constraints. So the first one is just ensuring that the sum of the incentive mechanisms over all the agents is equal to 0. So this is the budget balanced case. And the voluntary participation is just making sure that the cost of the player under the incentive mapping that we chose is less than the outside option, which I'm denoting here with this FI opt. We can relax these constraints if we so desire and ensure epsilon budget balanced or epsilon individually rational by just incorporating a relaxation term in either of these constraints. Additionally, we can change this budget balance constraint from just being a constraint to adding it as a term in the cost function. So in particular, we might take our incentive design step, and in addition to the update cost and the incentive cost, we now add a budget balance cost. And we add this voluntary participation or individually rational constraint. So the problem with doing this is that none of the results that I showed you hold anymore because we're changing the feasible set of parameters for the incentive update step. So what this requires is then a re-examination of the convergence results given these extra constraints. Okay, so now I want to tell you about a simple example, and this is an example that I really, really like because it's so simple and it's basically the core of a number of other problems. So this is the problem of coupled oscillators. So basically the idea is that you have two agents. They have a cost. They're trying to position themselves on a circle. They want to be near a desired location but as far away from each other as possible. A good example of this might be your two food trucks. You want to position yourselves on some circular roadway, which there happens to be an exact example of this in Minnesota, where food trucks literally try to position themselves on a big circle. And so you want to be near the place where most people come, but you don't want to be so near your competitor that people choose the other option over you. And so this location game, or this coupled oscillator game, shows up in, for example, synchronizing generators in, for example, microgrids. It also shows up in traffic light control. There's some nice recent work modeling traffic light control as coupled oscillators. It also shows up in robotics applications. So we'll say our two players have these costs, which I described. The first term is the term saying that they want to be near some desired location. The second term is saying that they want to be far away from the competitor. So now we're going to just analyze the case when there's no incentive. So we want to characterize the equilibrium of this game. So we have a non-trivial strategy space. We have a torus, which is another reason that this example is interesting. And so what I'm going to show you is that we end up with we don't have a unique equilibrium in this case. We end up with two equilibria. So basically, if we unfold our torus and we just look at this square where this first player's choice is on this x-axis, and the second player's choice is on this y-axis. And what I'm plotting in these lines is the zero derivatives. So these are the potential or candidate Nash equilibria. So zero derivatives for the first player are in the solid black line, and the derivatives for the second player are these dashed lines. Okay, so then what we can show is that if you just look at the intersection of these 2 points that I've highlighted, these are the points for which d omega, so the derivative of this of the vector of derivatives of each player's cost function is positive, and where omega itself is 0 for both players. And so what's interesting is if players are playing myopically and they initialize, let's say at any of these points that I've indicated with an x, we can determine by simulating the gradient flow of this game, which is just the derivatives of players' cost functions, and show that they converge exactly to these 2 points. And if we sample across the whole space, basically partitions the entire space, and they don't converge to any of these other potential Nash equilibria. And it turns out if you just assess these points and see whether or not they're Nash equilibria, these other intersection points, they're not, in fact, Nash equilibria. So we have 2 pure Nash equilibria, and they're the only 2 pure Nash equilibria in this game. OK, so now we're going to introduce a planner who's going to add cost to each of the players' cost functions. It's just going to be this last term, which has the parameters u1 and u2. And we're now going to optimize this cost for the planner. It's just a very simple cost. And determine the desired outcome. And then we're going to apply our algorithm to estimating theta while designing u to try to get the agents to converge to one particular Nash equilibria, which is this value x1, x2d. And what we can show is that if we now do the same plot, it turns out that in this game, there's one unique Nash equilibria. So through our design of these, doing our algorithm and designing u1 and u2, we've gotten rid of the other Nash equilibria. So we've made it so that there's only one Nash equilibria in the game. And it's nearby the desired outcome. And if we do the same thing where we sample throughout the space, we can show that, in fact, no matter where, if agents are playing myopically, no matter where they start, they'll converge to that Nash equilibrium. OK, so how much time? Oh, OK, so I might have time to get to the second part. OK, so I talked about this problem largely where we have a bunch of strategic data sources, and we have a planner who wants to make some operational decision, optimize this cost FP, let's say. And the way that they're going to do it is feedback a mechanism. So more broadly, they may have a bigger estimation task than just learning the parameter estimates of these players. They may also want to, for example, classify them so that you have a small number. So if you had a large number of players, for example, maybe they want to bin them into categories where you learn a model for a small number of agents. And so I want to talk a little bit further about the kinds of results that we have when we add in this extra estimation layer, or focusing more on just the estimation layer. So the first thing that we've been able to do is we constructed a social game on the Berkeley campus in which we had users compete over shared resources. So in this case, it was lights. They voted on their preference for the dim level of lights, and we gave them a reward mechanism, a lottery mechanism, that was implemented at the end of each week. And so we're taking this data, we're able to construct a framework in which we are able to make the utility at learning problem more robust. And so basically what we do in that case is we just learn the noise structure on the choices that the agents are making. So the problem with this framework is that it tends to be only work in batches, meaning that you can't do the online incentive design or estimation anymore. You have to do the learning step in batches. So the next thing that we did is leverage the correlations between players that we learn as a result of adding this noise term to our problem, and use that to create a new game in which there's pseudo-coalitions amongst players, meaning that we're treating players as jointly optimizing in some sense. And this, it turns out that with this, if we take a small amount of the data, learn the correlations between players, and then start construct cost functions in which players are playing according to these coalitions, then we can just use the simple gradient, online gradient, projected gradient update that I described previously to make a version of the game in which we have better performance of our estimators, adaptable to an online setting. Going one step further, It's the case that in general, players are not usually, especially individuals, are not usually playing exactly rationally. So we relaxed our assumption on the Nash equilibrium concept and added in some decision-making models from cognitive psychology. For example, this Luce-Shepard choice rule, which uses a softmax function. And we put this into a mixture of models or mixture of utilities learning algorithm, which we show has better performance than our previous estimation schemes. Okay, so what's next? So what we're looking at now, or where we're going in the future, is further into this assumption that players may not be rational. There's lots of results showing that at the individual level, it's the case that individuals tend to behave in a way that is less than rational, while at an aggregate level, using these risk neutral or utility maximization schemes tend to give good performance. So focusing on the individual, we're leveraging concepts from bounded rationality and prospect theory, which captures this risk sensitivity in players to improve our estimation schemes. And not just so that we can get better predictive performance, but so that we can make better insights into how players are actually playing and consuming resources. And why that's important is so that we can then design mechanisms that are targeting particular groups of people. Okay, in addition, we are combining active learning techniques, which allow you to purposely probe agents in the system to learn more information with these adaptive incentive mechanisms that I described. And we're applying these to multimodal choice data for urban mobility. And so we have data from a collaborator at Vanderbilt who they've constructed an app called Transit Hub that aggregates different modes, as well as Swiftly, which is a mode aggregation app based primarily in the Bay Area, but they're also available here. So if you want to download their app, then I will be happy to assess the data that you input. Okay, so now I have about 15 minutes, so I do want to talk about the parking example. So this fits in the same, this is a more recent work, and this fits in the same framework broadly in what we want to do. So we want to learn how agents are consuming parking resources and how that impacts congestion along roadways. There's lots of existing results that say that it's possible for people who are making parking choices to be circling and cause a significant amount of congestion in urban areas. And then what we'd like to do is work with the city to optimize the price of parking as well as information dissemination mechanisms such as dynamic message signs or what's provided on an app, for example, to reach particular occupancy and congestion targets. And so what I'll talk about now is just our recent work, which really just focuses on how do we come up with a model for how people are choosing where to park, and then how do we come up with a model for modeling this interaction between parking populations that are circling and congestion from throughput traffic going from point to point. Okay, so basically the flow of the problem goes as follows in this learning and optimization framework. So we have data from our partners at the Seattle Department of Transportation, and this data includes parking transaction data, so just paid transactions along a roadway, where the meters are located. We have land use information, for example, how particular areas are zoned, commercial versus residential. We have other economic indicators, such as fuel price and what is the minimum wage in particular areas, for example, or the medium income in particular areas. And we're going to combine all of this together to get a sense of how the parking resources are utilized across the city. So as an example of what we might do or what we have done so far, we've just taken a simple learning framework in which we create features based on arrival rates to particular blocks, where these blocks are located, and a histogram of how long people park. Turns out that in Seattle, most people tend to park for the full 2 hours. That's the largest proportion of people park for the maximum amount of time. And then we applied a weighted clustering algorithm just to divide the city to see, for example, do the natural or the neighborhood zones that the city already uses match what we see in terms of parking utilization. And it turns out that in some areas, you do see the clusters of blocks which match the already defined neighborhood. So for example, in this red area, which I believe is this Cherry Hill area, that's where a lot of hospitals are, and so there's a particular type of parking behavior that happens there because there's a significant number of disabled placard holders which park for free. So you see lower number of paid transactions, for example, in that area, and that comes out of the data. The South Lake Union area is also where the Amazon is located, of course, and so you can kind of see that neighborhood boundary come out. But some of the other neighborhoods are more amorphous and don't really match the existing neighborhood boundaries that we would see from the city level. So we took the arrival rates in each of these clusters, and we decided to model the behavior of parking in those areas as a queue. And it turns out that if you use a MGN queue and you simulate it, this behavior almost exactly matches at the neighborhood level the parking load that you see in the data that we have. And so our goal is to overlay a game theoretic structure on top of these neighborhood queues to say, okay, now people are deciding which block in these neighborhoods to park along. So I'll just describe the results we have very briefly for this parking or this queuing game where people decide which neighborhood to park in or which set of queues or which set of blocks to go to. So we can model this game as what's called a supermarket game. So if you imagine you're at the supermarket, you put a bunch of stuff in your buggy, you go to the front, and you decide which queue to get in based on what you know about how many people are in the line. Maybe you know the bagger and how quickly they bag things. You have information that you're making the decision based on. It's the same thing with parking. You get up, you say, okay, I'm going to go to a particular attraction, maybe the Chihuly Museum, and I want to decide which neighbor or which set of blocks around the Chihuly Museum along which to park. And maybe I do that based on information that I have. For example, it might be real information that's provided to me through, for example, an app, or it might be my past experience. So basically, users can make 3 decisions in this case. And they're as follows. They can either balk. They can say, okay, I don't want to drive. Maybe I'll use the bus or park in off-street parking, something to this effect. Or they join blindly. They don't decide to spend any time examining what is going on in that neighborhood, either through an app or through examining their past experience or something like that. So they just join blindly. Or they make an observation. They pay to have an observation. So the cost of paying could be, for example, paying a subscription to an app. It could actually be a fee that the city institutes. It could be a number of things. It could even be an incentive. You could think about it not as a cost, but as an incentive to have information. OK. And so I won't go through the theoretical details of this. I'll just show you an particular example where we compare. In the balking case, you can choose off-street parking only, or you pay to observe, or you just join blindly. And so what's interesting is that if we compute the Nash equilibria of this game, so I forgot to mention, this game we're modeling all the players as symmetric, so they all have the same cost, and this becomes a symmetric in-player game where we have a finite number of players. And so in this case, we know that there exists a Nash equilibrium by Nash's 1951 theorem. OK, so we can compute this Nash equilibrium by using a best response algorithm, and we can compare it to what the socially optimal outcome would have been. And so I think what's most interesting here is a couple things. So first off, if you look at this plot, maybe it's a little hard to read, but the dotted lines are the socially optimal for different balking, observing, joining. These are the probabilities that you will do these, take these actions. And the solid lines are the Nash equilibria. And so the probability that people will balk in the Nash case, so we're plotting it as a function of the traffic intensity here. So if you look for our queue, basically we have an arrival rate that falls between these two bounds, and this comes from the data that we have from Seattle. We took the service rate, mu, which is the time that you spend parking, the duration that you park. We took this to be the maximum, the 2-hour limit, because predominantly that's what we see. We just said that there's 30 spots across a handful of blocks for which we're simulating this game. And we would say the traffic intensity is comparing the arrival rate to the the service rate times the number of available spots. So this basically tells you what is the ratio of people arriving to people being served. So as it approaches 1, you're having the same number of people arriving to the system, basically as you're having served. And so that means that you have the potential for more and more congestion. OK, so if we plot our solution as a function of this traffic intensity, we see that the probability that people will balk in the Nash case stays 0, meaning that there's more people in the system than there would be otherwise, until you get to a very high traffic intensity. Whereas in the socially optimal case, people should immediately start balking or using off-street parking much earlier in the traffic intensity. Moreover, I think the most interesting thing is that you would expect that if everybody had full information, so everybody was able to observe, that would be the socially optimal thing to do. But it turns out that in the socially optimal solution, we only need to have a part of the population having access to information. And you can tell that by the fact that it's never equal to 1 in this plot. OK, so we also show the normal thing, that Nash is worse than socially optimal, which is only mildly interesting. But what is interesting is that according to other metrics, Nash has worse performance. And so these other metrics are things that tend to be used in practice. For example, the average waiting time, the time that you're spending circling, it's much worse in the Nash case. You see that it has this, as the traffic intensity increases, it has this sharp upswing, whereas the socially optimal case, the average waiting time is very low. Similarly, the utilization is much higher in the Nash case, meaning the probability of finding a parking spot is going to be much higher. The highlight of this slide is just that even according to metrics that are used in practice, the Nash is worse off. OK, so the last thing that I will talk about is our very recent work, which is work of Chase Dowling, who I mentioned at the beginning. And this is more of an examination of how do you actually model these parking queues, not just when you have parking behavior happening, but you also have the potential for other drivers to be along this road network. And so basically what we've done is create a whole new class of queuing networks. So classic queuing networks have queues at a bunch of nodes. For example, maybe these are different servers, like actual servers. And you have a packet or a job that arrives to that server. And once it's done at that server, it then gets shipped off to another node. But in our network, it's not services that are being transmitted from node to node, but rather rejections. So this creates a whole new kind of class of queuing games. And so basically, the way it works is that at the nodes, these are block faces, and we have parking queues there. And then along these edges, we have driving queues. So 2 kinds of queues. So a natural question to ask is, what are the conditions that guarantee the system is stable, which means that people will eventually park? So this is an important thing for example, a municipal service provider to ensure that there's enough access, and that congestion doesn't grow with bound. Another thing that's important without bound. It's another thing that's important. You don't want to have people jamming up the streets just because they can't find parking. OK, so what we're able to show is that if you have a very symmetric case where the input and output is the same degree for each of these nodes, which wouldn't be unreasonable if you were in a downtown area that had rectilinear blocks that had similar number of parking spots and similar arrival rates, which we do see in parts of the SDOT data, then we can show that as long as you satisfy some very simple conditions, so your arrival rate to the block has to be less than the service rate, and the road service rate needs to be sufficiently large, larger than some bound that is calculated by looking at the stationarity equations for this system, then we end up with a stable system, so we don't have this congestion growing without bound. And the average waiting time is this finite number. OK, so moving forward, we're interested in examining what happens if you have arbitrary topology, or at least topology that doesn't have this fully symmetric structure. And so in the symmetric case, the way that we were able to gain access to those results on the previous slide is that we leveraged the structure of the graph in reducing the set of equations that we had to solve to determine whether or not the system was stable. So we expect that we can do something very similar in the case where you have subgraphs that are very highly structured. The next thing that we're looking at is combining the 2 game theoretic results with this modeling results, so that we then can think about how we can design the incentives to be able to shape the arrival patterns to the different blocks, as well as how people are utilizing blocks in a city. And the most important thing, the most exciting thing, I think, is that we have plans to do testing and validation, which leads me to my last slide, in which the ultimate goal for this last part of this work is really to think about how we can construct a living lab. And so we're starting to do this with experiments in the downtown area on collections of blocks, where we're not only collecting data on the parking utilization, but we're also implementing intercept surveys to get information about how people are, what their experience is like in parking, for example, in terms of how long it takes them, what is their perceived time it takes to park. And once we've done this initial experimentation, we have plans to implement actual living lab experiments where we implement the design mechanisms that we come up with. And so just to conclude, I think that this space in general is very, very interesting, and I think that we're all living in Seattle, which is an amazing place in terms of the fact that the city is so jazzed about working with researchers on testing new things that are just going to improve everybody's daily life. And so I think that this space of looking at problems in smart cities is a really good and interesting space with a lot of very rich problems, both on the theoretical side as well as the practical side in which you can have real social impact. So with that, I'll conclude my talk.
Thank you, Lillian, for an excellent talk. So I'm sure you all enjoyed how a group of users can be understood and shaped for their behavior with appropriate incentive, as happens to you in your classes. If you have any question for Lillian, please go ahead.
A little bit about how the policy could be created to match the model. In other words, if you come up with a, let's say, an optimal model solution, how can you as a researcher interact with a policymaker to get policy that
Yeah, so that was actually I have a set of slides on this that I was going to talk about, and really those slides were basically motivating that this is a challenging problem that we need to think about, how we can work with policy implementation, or people who design policy and implement policy. And so what we're doing with the City of Seattle, with the Department of Transportation, is actually we've been engaging with them over time in conversations repeatedly to say, okay, well, what is the policy design process? How can our experiments that we're conducting actually have real impact? And I mean, I don't really have a good answer to that, but I do think that that's an important question.
I have a question for you. Slide number 26 or 27, I think. Yes. So you have got the conditions for the queuing, two separate conditions, right? One is the service and the arrival rate. That condition is known, and the other one is the service rate for the route. It looks like somehow you managed to get it as a decomposed separate results. Is it possible that you have a condition where combination of the...
No, those things really have to, they both need to be satisfied for this, yeah.
Is there a way to say the sum of the road service rate plus the service rate at each of the parking?
Yeah, so we've looked at that in the asymmetric case, and as I said, these is very preliminary results, and we haven't quite grasped exactly what needs to be done in the case where you don't have symmetry.
It looks like a decomposition.
Yeah, I don't think it's quite that easy. I mean, so the problem is that the rejections along the roads introduce additional equations that are not the same that you would get if you just were analyzing a regular queuing network. So you end up with a system of polynomials that's higher. It's not just a set of linear equations in the stationary probabilities. So you end up with something that's much more complicated. And we haven't, other than in the symmetric case, we haven't figured out what the right solution is for simplifying that problem.
Any other question for Lillian? Otherwise, let's thank the speaker again.